Okay. Well, let's start. First of all, today is the last lecture, and some technical information about exam. If you wish to have an exam, to pass an exam, then it will be a home exam, and I will send you several problems, and then most probably we discuss on Zoom at some moment when you are ready. But if you want to pass an exam, please send me a request to this mail. And then I send you some. Just write that you want to have an exam, and please write me whether you are going to have this exam in High School of Economy or in Skaltech. There are somewhat, or in both. There are somewhat different procedures, so please inform me what type of examination you want. Well, that's for some technical moment, and now let us start with mathematics. Last time I finished with the following theorem. I just want to recall that, and this theorem is our goal for today. I recall that starting from any Coxeter group, we constructed special cell complex which is endowed with metric. It is cut zero and hence contractible. And the group acts on this complex. And the theorem which I announced for today is that cohomology of this Coxeter group with group ring coefficients are isomorphic to cohomology with compact support of this complex with usual z coefficients. And actually I said that it is a general, and then I announced that we will compute this. I will give explicit, this formula is due to Davis. This theorem is Mike Davis. I forget the year, something about 1998, I guess. And I will give this explicit answer, but this part is more or less general situation when a group acts on a contractible space with compact quotient and finite stabilizers. And let us start with this general situation. So for some moment, let us forget about Coxeter groups and just we discuss some general. This is more or less homological algebra, general situation with homological algebra. First of all, we have already used these constructions at some point, but now let us do it more precisely. Suppose that we have a subgroup of a group G, arbitrary group, arbitrary subgroup. Then there is a notion of induced and co-induced modules. Namely, assume that M is an H module. Then we can construct a G module in two ways. First way is called induced module. We use the following notation: induced from H to G, and it is, by definition, we take group ring of G and take tensor product over ZH, or I can write just over H, this is the same, with M. First of all, what we mean here? I recall that we have two possibilities. We can take, well, ZG is a two-sided G module. We can act by G from left and from the right. So we can think of what is written in the following way. This is a right G module, this is a left. We have tensor product of a right G module and left G module, and then we still have action of left action of G. So we have left G module. Vice versa, we can consider this as tensor product of two left G modules. Then what we get is a right G module, but we have standard transformation from right G modules to left G modules, so we again get the same left G module. It is very easy to see that this is the same. So this is a definition. But we can do another thing. This is called co-induced module. We can take H equivariant homomorphisms. So for similarity, I write H also here. H equivariant homomorphism from the G to M. Again, when we mean H equivariant homomorphism, we must say, well, here there is more or less one natural understanding. We have left G module structure on ZG. This is also left module. So this is homomorphism of left but H modules, not over ZG, but over ZH. But we still have right module structure here, and it induces the structure of ZG module here. These two notions are in generally different, but there is a very easy claim I suggest you as an exercise. This is very simple exercise, that this is the same equality means that they are naturally isomorphic, provided that H has finite index. Well, just one can easily write down explicit isomorphism. This is more or less the same that when you have a finite dimensional vector space, then dual vector space is isomorphic to it. This is more or less the same. When you have a finite dimensional free module, then a dual module is isomorphic to it. But in general, this is not the case. Well, what we have in general concerning induced and co-induced modules? We have very easy but very important claim, which is called Shapiro lemma. Shapiro lemma, I'm sorry for my pronunciation. Well, it says the following, that we have natural isomorphisms. If we take homology of the group H with coefficients in M, then it is canonically isomorphic to homology of G with coefficients in the induced module. And similarly, if we take cohomology of H with coefficients in M, then this is naturally isomorphic to cohomology of G with coefficients in co-induced module. Oh, sorry. Well, why this is true? So proof. Let us take how to write down this homology. We need to take projective resolution of Z over ZH and then tensor it by M. But let us take projective resolution. Let F be projective resolution of Z over ZG. Then we can think of it as of projective resolution for H as well. And when we are interested in this homology, we need to consider the chain complex F tensored by M over H. Well, but when we are interested in this homology, we need to consider F tensored by over G with the induced module. But induced module is ZG. Well, it is very easy to see that this is canonically isomorphic to each other. Just very straightforward. And similarly, completely similarly for cohomology. Well, for cohomology, I will write it here. For cohomology, you have the following isomorphisms. This cochain complex is isomorphic to Hom over G from F to co-induced module. Okay. So this is very straightforward. Well, in particular, what one can easily see well, the terminology is as follows. If one says just G module is induced without any specification of a subgroup, this means that it is induced from trivial subgroup. So we always, any abelian group is module over trivial subgroup of G. So we can always induce from any abelian group. For any abelian group, we can consider induced or co-induced modules over any group G. So if let us look what says Shapiro lemma in this setting. So suppose A is just abelian subgroups. Suppose that H is trivial in this situation. So if A is abelian subgroup, and we have some module which is induced from trivial subgroup to G of A. Well, then look, here you have homology of the group H with coefficients in homology of trivial group with some coefficients. Of course, homology of trivial group lives only in dimension 0. So we immediately see the following, that homology of a group with coefficients in any induced module n is trivial in positive dimensions. And similarly, if n is co-induced, if n is co-induced, then cohomology, vice versa, cohomology of G with coefficients in n are trivial in positive dimension. This is direct consequences of Shapiro lemma. Now, what is obvious? What is obvious? Obviously, if we take, now let us return to arbitrary group H, subgroup H. If we take a module ZH, well, just this H module, and consider induced module, what is this? This is, of course, ZG. Just a trivial situation. This is general and very simple fact, completely obvious. But if we take this, the combination of this standard, of this very easy fact with this exercise, then we see that if H has finite index in G, then this is also true for co-induced module. In general, not, but so let us fix this. That we have corollary that if H has finite index in G, then ZG is co-induced module over ZH. Well, now what Shapiro's lemma say in this situation? Shapiro's lemma say that corollary of this corollary is that cohomology of H with coefficients in ZH are canonically isomorphic to cohomology of G with coefficients in ZG. So cohomology with group ring coefficients are, they do not change if we pass to a finite index subgroup. They do not feel such finite things. So they depend on the group. They can be non-trivial, but they, if we pass to a subgroup or supergroup of finite index, then we get the same. So in particular, of course, there is nothing interesting in the case when the group is finite. If G is finite, then this is the same as cohomology of a point. So this is Z in 0 dimension and 0 in positive dimension. So this is for sure not interesting in for finite groups. Of course, we have the same isomorphism since we have this general. This is true always. So of course we have the same for homology, but it is not interesting since we have 0 on both sides. But for cohomology, it is interesting since this is very non-trivial invariant of a group, but this non-trivial invariant doesn't feel such finite things. Okay, and so this is the first general fact. Second general fact is as follows. Well, second general theorem is as follows. Suppose that G acts freely on a contractible CW complex X. Let it be freely and cellularly. I don't want to discuss general situation. Freely and cellularly on a contractible CW complex X, so that the quotient is compact. Well, of course, the CW complex is compact if and only if there are finitely many cells here. Okay, then we have this general isomorphism. Cohomology of G with coefficients in group ring, in the group ring, are canonically isomorphic to cohomology with compact supports of X just with Z coefficients. Cohomology with compact supports, let us consider the general definition. Well, we can just consider cellular cochains, cochain complex, well, and okay, a cellular cochain, we have, of course, it is interesting when the group is infinite. Otherwise, everything is trivial. When the group is infinite, then complex is, of course, also infinite. If a group acts freely, so each element acts non-trivially on all cells. When complex is infinite in each dimension, then of course a cochain may be non-zero on infinitely many cells. But here we have compact support cochains. This is just the subgroup of cochains which are non-zero only on finitely many cells. So this is the set of all cochains. This is cellular cochains. And this is the set of all cellular cochains such that phi of sigma is 0 for all by finitely many, for all but a finite number of sigmas. This is the definition. This is a cochain complex, and this is cohomology of this cochain complex. There are standard facts. It is more or less standard that actually we know that usual cohomology is independent of the cell structure. We can decompose complex in different ways, and we get the same cohomology group. Similarly for these, actually there is a canonical definition which doesn't appeal to cell structure at all. We can take singular cochains and singular cochains here, but then this is not a correct definition. A correct definition is that we take those cochains that are trivial for all sigmas that are not contained in some compact subset. So that there exists such compact subset K, that the cochain is non-trivial only on simplices which are contained in this K. Okay, so anyway, this definition is completely enough for me. Well, look, if you before proving this theorem, let us note that these two theorems together, this theorem and this corollary, yield the following. So corollary, in this theorem, we can, instead of free action, we can consider any action with finite stabilizers. So suppose that G acts on X with finite stabilizers of cells. And this is instead of freely, and everything else is the same. I claim that then well, the same conclusion. So theorem is still true. Before proving this theorem, let us deduce this corollary from it. It is slightly non-trivial. It is not just in one sentence. So let us prove this corollary from that theorem, and then I return to the proof of the theorem. Well, if a group acts on G with finite stabilizers, then look, we know that the quotient is compact. So we have only finitely many orbits of cells. So since we have finitely many orbits of cells, hence we have only finitely many types of stabilizers up to conjugacy, up to conjugation. Of course, if two cells are in the same orbit, then their stabilizers do not coincide, but they are conjugate to each other. So we have finitely many. Finitely many stabilizers up to conjugation. And let these stabilizers be H1, HK. Now there is a standard fact that each subgroup of finite index contains a normal subgroup of finite index. If we have a subgroup of, if we have a group G, and G has a subgroup of finite index, then we can find a smaller subgroup which has finite index in G and which is normal in G. This is just the intersection of all subgroups conjugate to H. So we can find here smaller normal subgroups of G. And then these subgroups are contained in any stabilizer of a cell. A stabilizer of each cell is conjugate to one of these subgroups, hence contains one of that subgroups, one of those subgroups. So for each cell sigma, there exists I such that stabilizer of sigma contains an I. Okay. Well, no, they are finite index. Oh, sorry. Что я говорю? Sorry. One moment. Oh. So sorry. Just. Well, it's my standard problem. I always confuse orders with well, actually my first intention was not to prove this corollary, and this is this is exactly what I wanted to say, that this will be all obvious for Coxeter groups, and then let us change the this is a problem. This is not a general problem. People know how to prove this. This is problem for a good problem for you if you want to understand this properly. That this is true. I will not prove this in general setting, but we will see soon that this is true for the Coxeter group, and that's enough for me. Well, let us prove this theorem. So this is not the proof of this problem. Let's proof of theorem. Okay. Well, actually, for the proof of theorem, let us understand just the algebraic version, and the algebraic version will be completely trivial. So lemma. To formulate lemma, I need one notation. Assume that M is an arbitrary G module. Then I can consider the following group. It is complete analog of such chains. By definition, this is the subgroup of all homomorphisms from M. So sorry. Well, just to arbitrary abelian group, but I need to Z. We can take all homomorphisms, just homomorphisms of abelian groups from M to Z with the following property, that for each M in this M, there exist only finitely many. We can consider the value of phi on G applied to M. Well, and the requirement is that it is 0 for all but a finite number of G. So this is just notation. And what lemma is the following, that for any G module, we can consider such two things. We can consider G equivariant homomorphisms from M to the G, or we can consider homomorphism from M to Z, but only this compact support. And these are canonically isomorphic to each other. Let us understand that why this is true. This is true since we can easily construct a map from right to left. Well, how to construct a map from right to left? Suppose that, so this will be psi. Suppose that we have such a homomorphism phi. Then the resultant homomorphism is a homomorphism from M to the G. Well, the resultant homomorphism its value on some element M is as follows. It is the sum over all G in G. I think it is like that. I'm not completely sure about this G inverse, but it seems to be like that. The sum is well defined because of this finiteness property. Let us check whether this is our goal is that this is G invariant. Well, if we apply psi of phi to some hm, well, then this is the sum over G of G inverse H M G. Well, and this is the same. Now we can consider the inverse of this will be a new element. Yes, we consider element K, which is H inverse G. Okay, and then we get sum over K of phi of K inverse M multiplied by well, and then G, of course, is HK. Well, so HK. And that's exactly what we need. Here we can redenote K by G. And we get exactly that this is H multiplied by psi of phi of M. So yes, that's correct. And the opposite, this is in this direction. In opposite direction, you need just to take the coefficient to an element M. You assign an element of a group ring, and just you take the coefficient of unity in this of the identity, and that's the value. So this is true. And now let us understand that this is exactly what we need. Indeed, now how to prove theorem using this lemma. What we see, since the group G acts freely on a contractible complex X, then we see that cochains of X, all cochains of X, is a free resolution of Z over ZG. First of all, this is cochain complex of G modules. G acts on X and hence acts on cochains. So not cochains, chains of X. This chain complex is a free resolution of Z over ZG. Indeed, this is a chain complex of free ZG modules, and its homology is as homology of a point since X is contractible. Well, so if we are interested in cohomology of G with coefficients at G, then cohomology of G with coefficients in ZG, we need to take this resolution and take home from it to ZG and take the cohomology. So this is the cohomology of home from, well, I will not write Z here just for simplicity. We take home over G from this resolution to ZG. Well, but now we can use this lemma. This is the same as this complex inside. This is the same as homomorphisms with compact support of C star of X to Z. But this is exactly such cochains with compact supports. So this cohomology with compact support of X with coefficient in Z. Well, this property and this property are just the same. Yes, of course. This is very, very natural isomorphism. It commutes with everything. Well, so we have proved this theorem. Now let us focus. Let us return to let us return to Coxeter group. Okay. Now we have this situation that this is a Coxeter system. With finite number of generators. Well, actually, there is the following general property. It is called Selberg's lemma. this is a very general statement that any finitely generated group of matrices over a field K of characteristic 0 has a torsion-free subgroup of finite index. This general fact, of course, I will not prove this. This is from different part of science, but this implies, in particular, then a Coxeter group, any Coxeter group, has a subgroup of finite index, a torsion-free subgroup of finite index. In fact, for Coxeter groups, it is even easier than for general linear groups. So I'm not going to give you this as an exercise, but this is a good exercise. That this is not completely trivial. We have I have pointed out a torsion-free subgroup in the case of a right-angular group. Then we can just commute all generators, and we automatically have such torsion-free subgroup. But in general case, it is not so easy, but still it is a good exercise. Once we have this exercise, we actually see that we actually can pass from, we can avoid this problem. We can say that, okay, Coxeter, for a Coxeter group, we do not have a complex when, on which the action is free. We have a complex on which the action is on which W acts, but we do not know whether the action. Moreover, we know that the action is not free. Well, it has finite stabilizers, but actually we know even more that these stabilizers are more or less bounded altogether. Indeed, in this case, we see that well, in this case, what do we see? We see that so if W has a subgroup gamma of, we know, if we have proved that W has a subgroup gamma of finite index which is torsion free, then of course the action of gamma on sigma is free. Why? Because yes, gamma has no elements of finite order, and well, yes, I'm so sorry. From the constructions of sigma, from the construction of sigma, we easily see that an element of well, what we see from the construction of sigma. I recall that sigma was constructed as follows, that for each I recall that we have such notation as F is the set of all subsets, so that induced group WT is finite. Well, and the action of T, the action of the complex sigma is constructed as follows, that for each left coset of WT in W, for each finite WT and for each left coset, we have such cell. This is a cell with with this. This is a convex polytope. With this number of vertices. This is the convex polytope with the number of vertices WT. So we have cell. We have this cell. Okay. For each such left coset, and the union of all these cells is the complex sigma. So if a point here, any point in sigma lies in a relative interior of some cell. So suppose that point lies in a relative interior of this cell, then if an element W, if an element G stabilizes P, then in particular G stabilizes this cell. So GW sigma omega T equals W sigma omega WT. Well, and what we see? We see that G, hence GW inverse GW belongs to the group WT. Well, so we necessarily see that G is conjugate to an element of a finite group, so G has finite order. So if an element stabilizes at least one point in sigma, then it has finite order. So if we take a torsion-free subgroup, then it has no element of finite orders, so it acts freely.
So it's not true that W acts in sigma is finite stabilizers.
It is true. But this is more. The fact that there is a torsion-free subgroup of finite index, yes, of course, this is exactly the proof that W acts on sigma with finite stabilizers. So hence, any torsion-free subgroup acts freely. Yes, this is the same. So what we see? We see that from general theorem, which we have proved, it follows, first of all, cohomology of the Coxeter group with its group ring coefficients is isomorphic to cohomology of this finite index subgroup. I do not need any information, any explicit information on how this finite index subgroup looks like. I only need its existence. And hence, it is isomorphic to such compactly support cochains of sigma with coefficients in Z. So we know this. And next step is the the computation, and the explicit computation of the right-hand side, and hence of the left-hand side. Okay. So before formulating this result, now let us discuss this computation. Before formulating this result, let us recall some yes, first of all, I want to say that instead of the Selberg's lemma, we could use that problem which I raised here. So if we have proved this in general context, then we immediately have this isomorphism. But nevertheless, this is... I forget to say one important thing. Why Coxeter group is... why it is finitely generated? It is finitely generated, but why it is group of matrices? The matter is that I recall that we have considered such matrix last time we discussed what happens when it is positive definite or almost positive definite. But in general case, we can consider vector space R to S with this scalar product. Well, I don't want to think whether it is positive definite or degenerate or anything else, and then any S goes to any S in generators yields the following reflection. Any vector goes to our basis vectors are numbered by elements S, and we can write down such formula. Then these elements, then there is these elements satisfy all relations, and we get a linear representation of Coxeter group. In fact, there is one point which I don't want to discuss, but actually it should be proved. It is not so trivial that this representation is faithful, that it has no kernel. But it is true. Hence, Coxeter group becomes linear group, and hence it has a finite index subgroup of torsion-free subgroup. But for a Coxeter group, it can be proved directly. Well, let us continue. So now I want to erase all this and discuss computation of I want to start. I want to recall how the action of a generator S on sigma, how this action looks like. Last time we have proved the following. Well, first of all, last time we have proved the following statement, that there is a mirror HS, which is totally geodesic subspace of sigma. HS is totally geodesic. I always use that sigma is ket 0, so it has unique geodesic from every 2 points. HS is totally geodesic, and HS decomposes sigma into 2 parts. Into 2 parts. And actually, I need the following, well, vertices of sigma are elements of W. So we have vertex 1. And of course, we have vertex S. And of course, these 2 vertices lie on different sides. The geodesic between them is just an edge, and it intersects HS. Now, an easy observation that we can easily characterize which points lie on the left side and which on the right. The characterization is as follows. For a point x, well, so sorry. Well? Yes. I have this. I want this characterization only for vertices. I don't have length for a point. I have a length for an element W. Then W lies here. Look, if I have W here and I have SW here, then we have this situation if length of W is less than length of SW, well, and we have opposite situation when it is vice versa. But for points, we also have one characterization. Look, but it is more geometric. A point is on the left if its geodesic to 1 doesn't intersect HS. And this geodesic intersects exactly once. Just an easy observation that, of course, we cannot intersect HS twice or more. Because if we intersect twice, then the geodesic totally lies in HS. Okay. This is what we need. Yes, in fact, I also need some group property of Coxeter groups which I don't want to prove. I'm sorry for that, but I gave you some reference to Bourbaki, which is very good if you are going to understand the combinatorial structure of Coxeter groups. I recall that we have, first of all, you have this Coxeter system, Coxeter group with standard set of generators. And for each T in S, we can consider the subgroup generated by only those elements from T. So then the first claim, which I have already used last time, is that this is again a Coxeter system. So we have no additional relations. We have already used this. But actually, we can say more. What we can say more? We can say that when we pass from Wt to W, then we get no new conjugations. I need the following. Suppose that two elements of Wt are conjugate in W. I claim that then they are conjugate in Wt. This is true, but I'm not going to prove this. So, my claim is that if two elements of Wt are conjugate in W, then they are conjugate in Wt. And also, third fact is that no element of Wt is conjugate to a generator S, which is not in T. Is conjugate to a generator well, once more, I'm sorry, but I do not have time to prove such more or less combinatorial facts. So let us assume that this is true. In fact, why do we need this? We need this to analyze properly this situation. So suppose that some element G stabilizes a cell. Well, then we see this situation. Well, I'm interested in particular case when G is just a generator S. So if a generator stabilizes a cell, this cell, then I get this situation. And I get that W inverse SW belongs to Wt. And using these two claims, I can say that first, this implies that S belongs to T. It is not possible that a point here is stabilized by some other generator S. A priori, it could happen that okay, we have this this subgroup, but some others generator S stabilizes this cell. It doesn't happen. And second, we see that this element, though W can be not in Wt, we see that this element is conjugate to S in Wt. And hence, in this, hence it is just standard reflection, one of the reflections. I recall that, let us recall that for finite group W, yes, this sigma W is just a polytope, which is denoted, we take this standard faithful representation by reflections in the orthogonal group. We have constructed it. It is a kaleidoscope on a sphere. And sigma omega, we just take I recall that this representation is constructed by taking a simplicial cone and reflecting it. And then we get this kaleidoscope on a sphere. And then inside of this cone, we can choose a point which is on distance 1/2 from each facet. And then sigma omega is just the convex hull of the orbit of this point. And the most instructive example is this 60-degree case. We here take the point with distance 1/2 and get a regular hexagon with side 1. Well, so this is a typical example how sigma w looks like. And for any sigma w, we have plenty of these reflections. They correspond not only to generators, but they correspond to elements conjugate to generators. And this easy argument says us that any situation when an element stabilizes a cell looks just in this way. So generally, when a generator stabilizes a cell, this means the following: that this mirror HS looks like very easily, namely, look, for each, let us characterize this HS completely. I will give the answer. I will give it here. The situation is as follows: that for each T in SF, and for if we take T in SF and we take W, then we can consider cell W sigma omega T. If it happens that W inverse SW belongs to WT, sometimes it happens, sometimes not. If this is not true, then our mirror doesn't intersect this cell. Our mirror goes not from through all cells. But if it is true, then we have here one of the reflections of these standard reflections corresponding, and HS inside this cell looks exactly like this mirror. And this is the mirror corresponding to, we have mirror, we have standard mirror corresponding to S in the initial sigma omega T, and then action of the element W takes this picture to that picture, takes this mirror to that mirror. And our claim is that HS, the total mirror of an element S on sigma, is union of such mirrors inside faces, is union of mirrors in cells satisfying this condition. This condition. So, okay, we have this characterization. Okay. Yes, and now, okay, we have these mirrors for generators, but I would like to introduce let us introduce the following notation. We denote by R the set of all conjugates of elements of S. So we have the group W, we have its generators, the set of generators S, and we denote by R all elements conjugate to an element of S. So this is the set of all elements conjugate to elements of S. And of course, well, if we have these properties for S, then we have the same properties for elements R. So we have HR, this is mirror for R, and we have all the same properties. It decomposes into two parts. Just this situation is conjugate to that. So if they are conjugate using some element W, then the action of W takes one situation to another. So we have all these facts. And locally, it looks like that. So everything, all the things are true. And now, last time I formulated the following fact, and now let us discuss it in more details, that assume that we have an element W small in W capital, and this element we interpret it as a vertex of sigma. And somewhere in sigma we have an element 1. And we can consider all mirrors HR that separate 1 and W. We have some mirrors between them. For each R, we can ask whether 1 and W are on the same side or on different sides. And we can compute the number of R small such that HR separates 1 from W. And the claim is that this is exactly the length of W. Let us understand why this is true. First of all, well, let us understand which that such inequality is obvious. Indeed, consider if we take 1 and S, then they are separated by a single mirror HS. Well, let us act on this by an arbitrary element W. Then we see that for each element W, W and WS, where S is a generator, are separated by a single mirror. Which mirror? WR W inverse. WS W inverse. This is the only mirror. This mirror separates them, and no other mirror separates them. Just this situation is taken by the action of W to that situation. So we see that for each element W, there is exactly one mirror separating W from WS. Now, well, if we can write down W as S1, S2, etc., Sk. I do not require that these are different. These are just any generators. Maybe they repeat, maybe with the repetition. But then, okay, we can go from 1 to W in the following way. I first go to S1, then to S1, S2, then to S1, S2, and S3, and so on. Well, and each segment intersects exactly one mirror. So what I see? I see that I find a path from 1 to W which intersects exactly k mirrors. So, of course, we see that maybe this path may be like that. Maybe I intersect some mirror twice or several times. It is possible. But definitely I intersect all mirrors which separate one from omega W, so we get this estimate. To get another estimate, I want to be not very precise. I just say an idea. An idea is that I can consider a geodesic between 1 and W. And this geodesic doesn't intersect extra mirrors. It doesn't intersect a mirror. It cannot intersect a mirror twice or more. So intersects exactly this number of mirrors. If it intersects these mirrors in then I can write down the corresponding word. There is a difficulty when it intersects several mirrors in time, but it is not so hard to avoid it. We just can deform. Actually, this is not even, this is a complete proof. We take a geodesic, it intersects exactly this number of mirrors, no extra mirrors. Now we slightly disturb it so that intersects all these mirrors, not two mirrors at the same time, or only one mirror at a time, but it still intersects no extra mirrors since we disturb it slightly. And then we write down the corresponding sequence, so the corresponding path. And we get a representation of the same length. So, well, we have this equality. Well, and
why do we get the same length?
well, first of all, if we have some representation in this form, then we have this inequality. Well, but then starting from then we can consider a path corresponding to a geodesic. And then we get opposite inequality.
Can't get a sequence shorter.
Yes, yes. Well, so this is just equality. Oh, well, okay, I think this is a good point for to have a break. Let us have break till 6 exactly, and then proceed. Well, let's continue. So I was asked about what the answer will be, and that's the good point for saying this. But to say this, I need one additional thing. Look, I'm interested in a neighborhood of 1 in the complex sigma. How it looks like? Well, it is rather easy to say how it looks like. If we take 1, then, first of all, we can easily say how many edges go from this 1. Edges going from 1 are in one-to-one correspondence with generators. So these are just all different elements of the set S. This is concerning edges. We also know all cells containing 1, namely, okay, we know that all cells look like that, but cells containing 1 look just like they just corresponding to some subgroups which are finite to those T. But so, and for each Si, we have this mirror. This is HS1, this is HS2, this is HS2, and so on. And it is very natural to consider the region bounded by all these mirrors, to consider the region which is 1 and all points which can be achieved without crossing a mirror. This region, it is not a cell generally. We can have difficult combinatorics here. But we can always say that topologically first of all, we denote this by K. This is the region bounded by all mirrors. And first of all, topologically, K is contractible because it's a cone from 1 over its boundary. First of all, let us understand over which is this cone. Well, we have here as many cells as the number of finite subgroups, or finite standard subgroups of. We have a cell for each T in calligraphic finite. So we have as many cells as the number of finite subgroups of the form omega WT. And what we have inside each subgroup. Inside each subgroup, we have a cube. Combinatorially, this is a cube. This is a rather easy exercise. We know that this cell is a simple polytope, and we take orthogonals to edges, and so this is combinatorially a cube. It has front surface, which consists of this is front surface for that cube. It consists of parts of faces of this cell, and it has back surface, which consists of parts of mirrors. We can look on this in two ways. Topologically, K is homeomorphic. Look, this cube, we can inscribe here a simplex. In this case, it is a segment, but we can, in general case, we take the, I just write down what happens in three-dimensional situation. if we have front surface of cube, this so this is 1, and we have front surface is the union of faces containing 1, and back surface is the union of faces not containing 1. So then this back surface is parts of mirrors, and front surface is like that, and we have here such triangle. And topologically, this cube can be projected onto this triangle homeomorphically, onto the corner over this triangle. So topologically, up to homeomorphism, we see that this is the same as cone over the nerve of the Coxeter system. I recall that nerve is just simplicial complex spanned by generators with simplex spanned by T if and only if the group is finite. In fact, it is better to say that it is a cone over the barycentric subdivision of this nerve. The matter is that it is convenient to decompose, it is not convenient to do like that. It is more convenient to decompose this, and here we have cone, barycentric subdivision of that is canonically isomorphic to what we see here. In this situation, we need to add these 3 diagonals, and we see that the back surface is exactly a barycentric subdivision of 2 simplex, and similarly in arbitrary dimension. So this is just combinatorially. If we take this, and this K is called a chamber. So we can look on our sigma in 2 ways. We can say that sigma is decomposed into cells. This is sometimes convenient, but not always. The matter is that these cells are different. We have different types of cells corresponding to different types of subgroups. This is not so convenient. It is better to have the same type of chamber. We have now for each vertex W, if we consider its chamber, those points which are inside the region, then it is just W applied to K. So all chambers look in the same way. In a sense, this is a dual decomposition for decomposition into cells, but this is not decomposition into cells. These chambers may have difficult, complicated topology and combinatorics, but it is convenient to consider them. And we understand it combinatorially. And one more. What is the boundary of this chamber? The boundary consists of intersection, is the union of intersections of this chamber with mirrors. The boundary is union of such intersections, and it is natural to introduce some notation for these intersections. So let us say that Ks is just the intersection of K with mirror. And we easily understand it just combinatorially. It is the star of S in this barycentric subdivision of the nerve. S1 is here, and this intersection is the union of all simplices containing this point. But synthesis of barycentric subdivision, we take only this part, not the whole one. So we easily understand, if we are given a Coxeter system, we immediately can construct this complex and these subcomplexes. And now two more notations. Assume that we have an element W small of the Coxeter groups. Then we can, to this element, we can assign two subsets of S capital. First of all, the first one will be denoted by QW. It will be for each S in S capital, we can ask whether what is greater, L of WS or L of W. And we say that this is Q of W, and T of W is vice versa. One of the, I recall that one of the inequalities is always true, since they have different parity. Well, and the last notation is that when I have several several complexes Ks, I can take the union of them. And just Kt is the union over S and T, just notation. Well, now I'm ready to formulate the answer. Theorem by Davis is that cohomology of Coxeter group with group ring coefficient, which is the same as cohomology with compact support of this sigma with z coefficients, has the following form. It is direct sum over elements of the Coxeter groups. And here we need to write the following. We take cohomology, usual cohomology, of such pair of simplicial complexes. K, sorry, here I have T of W, this T of W. In other words, this can be rewritten in the following way. Okay, we have only finitely many possibilities for T of W, since we have only finitely many subsets of S. So this is the sum of T, and for each T we need to take, I denote like that, well, this is the set of all W with the given T of W. This is just the free abelian group generated by this set. And so we need to compute only finitely many cohomology groups, and these are finitely groups. These are cohomology groups of finite simplicial complexes. So we have, well, for any given complexes, we can easily compute them. So this is purely combinatorics of the nerve. This is not combinatorics of the nerve. This is something involving some combinatorics of the whole Coxeter group, but not so hard combinatorics. Involving only lengths. Okay, so that's the answer. No, these are cohomology of pairs.
Oh, okay.
They can be. And so this is just one. There are several results of such type when cohomology of certain global things involving Coxeter groups or similar groups are reduced to some combinatorics of certain subcomplexes. This is just one result of such kind to illustrate how it works. Okay, so let us understand why this is true. This is our goal. Okay, to start with, let us understand the geometric meaning of that Q of W and T of W. What is the geometric meaning? Once more, consider unit and consider any element W, any vertex of sigma. And here we have a chamber WK. Well, bounded by some mirrors. And this chamber is just a copy of the chamber which is around 1. So it looks like completely in the same way. Well, this chamber K, the action of W gets K to WK. Look, if we look on all mirrors that bound this chamber WK, some of them separate W from 1 and some not. I claim that those mirrors which separate W from 1, for instance these two in this, well, mirrors that separate W from W, each mirror, if we take for each mirror there is an edge. If this is a mirror HR, and R is conjugate to S, so if this is mirror WS W inverse, well, these mirrors are conjugate to mirrors. These mirrors are just HS. These mirrors are conjugate to HS with this particular element W. But they are obtained by conjugation of this particular W. So if this is, then the corresponding edge leads to WS. So if this WS is shorter than W, then this mirror separates W from 1. Then getting from here to here, we decrease the number of mirrors separating these from 1. And if it does not, so these are exactly mirrors, mirrors which separate exactly corresponding to Q of W, and all other mirrors corresponding to T of W. So Q of W are these, and T of W are those which do not separate. In fact, here there is one inconvenience. It is not so. In fact, we always should identify this one with this one, but it is more convenient to draw them here. So to be this is not HS. This is H conjugate to S, but for S in QW, Q of W. And these are H conjugate to S for S in T of W. Well, but then this is exactly the subcomplex KT of W. And what stands here is exactly the relative cohomology of the whole chamber with respect to the union of all those its faces. Okay, what is an important lemma? An important lemma concerns, well, this is T of W, but let us look on the complement on Q of W. Then there are two important claims. First of all, this Q of W belongs to SF. If we take those if this is purely combinatorial claim, that if we take a Coxeter group and for an element W we take the set of all S with this property, then the set of all these S generate finite subgroup. And second says about the union of all these faces. I claim that it is contractible. The first standard way is to prove the first and then understand the second from it in this direction. I will go in opposite direction. Let us understand that the second is immediate from what we have proved. The second is easy. Why? Look, take any point inside this chamber, any point P, and connect it with 1 by a unique geodesic. Well, I claim that it, and look when this geodesic leaves the chamber, I claim that it is inside this union. Indeed, if it leaves it, if this geodesic goes like that, then at this point we increase the number of mirrors separating our point from 1. But this is not the behavior of a geodesic. The geodesic always decreases this number. So what we see? We see that there is a retraction from the whole chamber to this union. Of course, this is a retraction, since if we take a point in this union itself, then it leaves immediately, and we are here. So just we see that there is K retracts on K Q of W, and well, we are done, since a contractible complex K is a cone. So K is contractible. It retracts to a subcomplex. This subcomplex must be contractible as well. Well, all homotopy groups must be trivial, and it is a CW complex, so it is automatically contractible. So we see this one. Well, how to obtain the first one? I have not so much time, so I will be somewhat brief. The idea is as follows. Let us consider a geodesic from 1 to W. And now let us start let us start projecting it onto mirrors. We can just, well, if we have in cut zero space, if we have a total geodesic subspace, then we have a unique geodesic from a point to this totally, the shortest geodesic to this point. And we can project 1 and W onto, say, the first mirror. Well, and look, after projecting on the first mirror, we still must intersect the second mirror and all other. Then we continue projecting, and it turns out that we always must still intersect the other mirrors. Hence, we see that these mirrors have a non-zero intersection. If they have, since they have a non-zero intersection, it follows this. I understand that I'm not precise here. Let it be a problem for you to deduce first from the second. Actually, there are several possibilities to do this, not only what I mentioned now, but still. Okay. So, in fact, it is. We can now rewrite the answer in an easier way. It is better. I denote. I prefer to take sum not over t's but over q's, and then I want to say that we need to consider only those q's which are in SF, and here to take this one and this one. This is the same. Just I want to say that we need to take only in this sum. We need to take only those t whose complement spans a finite subgroup. Okay. Well. Now. Let us study in more details. To prove the theorem, let us study in more details how reflections take a group, a subset Q in SF, and look on reflections corresponding to elements of this subset. Well, there are finitely many of them, and there are finitely many. I want to consider the following. I want to take Q in SF, and I want to consider the group WQ generated by only those reflections which are only those S which are in Q, and I would like to consider, let it be RQ. This is the set of all the set of conjugates of elements of Q in WQ. Okay? I considered this was the set of all mirrors in the whole group, but now let us restrict ourselves only to Q. What we see, consider 1. And I consider only those mirrors which correspond to this RQ. Well, sorry for a moment. No, not one. Sorry, this is a bad picture. Well, I'm sorry. I would like to consider 1 and all W in WQ. I have this finite subgroup, and let us consider all these elements, all these points in sigma. Well, we see a finite Coxeter group. So some of them are generators, and we have such mirrors. So we see a picture which resembles the picture for a finite Coxeter group very much. But just the intuition is that we also have this direction in which something else happens. So this is not all. Our sigma is much huger than what is written here. But I can consider only those those mirrors which correspond to R in RQ. And then the picture is just as for Coxeter group, finite Coxeter group, WQ. We have finitely many such mirrors. These mirrors, each of them separates our sigma in 2 parts. And so, totally, we have elements of WQ, and our sigma is separated into parts which lies, so to one it corresponds some cone. These are all, what is dashed? Dashed is all points which are not separated from 1 by all such mirrors. And similarly, for each W in WQ, we have the same cone, which points which are not separated from W by such mirrors. This cone can be, it is not so easy. It is something complicated, but I have this decomposition. And look, this decomposition is, of course, just this cone is the quotient of the total space by WQ. So let us denote this cone by BQ. And no, not big. I prefer let it be positive cone corresponding to Q. Sigma Q plus is this cone, and I claim that this sigma Q plus is of course sigma quotient by WQ. Indeed, I take any point, and its orbit intersects this sigma Q plus in exactly 1 point. That's exactly means that this is the quotient. What is important for me? Important for me is that this is the quotient by a finite group. And what does it mean? This means that well, we have, of course, we have the projection from sigma to sigma Q plus. If we have a projection, then we always have a pullback in cohomology. But if we have a projection along a finite group, then we have as well a pullback in cohomology with compact supports. So we have such natural pullback. So PQ is projection from sigma to sigma q plus, and PQ star is the pullback from cohomology with compact supports of sigma q plus to cohomology. Coefficients are integral. I don't want to write them down to this cohomology. Okay. In fact, look. Well, one short notice. Note. Sigma is a cell complex, but we can always take its barycentric subdivision and obtain that it is a simplicial complex. Just we introduce a vertex in the center of which. So let us think of sigma as of simplicial complex. Then why this simplicial structure is better than all others, than the cell structure? Since chambers become subcomplexes, everything becomes subcomplexes. And then this is just a simplicial mapping. Simplicial. And so we actually have this not only on level of cohomology, but we have this even on level of cochains. Just for simplicial cochains, we have for cochains the same pullback. Okay, this will be it will be convenient for us to have this. Okay, now look, let us look here. What is this? These are exactly those mirrors which correspond to elements of Q. Here we also have elements, mirrors corresponding to elements of Q. They are just shifted by W. This picture corresponds to that picture just by shift by W. We shift it here, and what we see? We see that this cone is exactly sigma q of W plus. So sigma q of W plus is such cone containing our cell, and moreover, the intersection of the boundary of this cone with the cell is exactly q of W. What we get? We get the following. We see that if we take a pair K and K T of W, okay? This pair, well, here in this situation, look, we have a chamber corresponding to 1, and it is in the corner of this cone. Well, let us denote in some way the union of all other chambers inside this cone. Let it be Xi Q. It is the subspace of sigma Q plus consisting of all other chambers. Then here and also here, I say that this is easily embedded into such pair sigma q plus just this chamber, and this is embedded there. And moreover, it is embedded so that, of course, their relative cohomology just coincide. Okay, but now, of course, and even again I can write down this on the level of cochains. Well, these are simplicial. Just all others are not important. Then this one easily goes to compactly support cochains of sigma q plus. The matter is that we have only finitely many cells which are not in Xi. Then by P star, by those map, we get into C star of sigma q, of sigma. Well, to be honest, if I write down like that, then, well, one need also to consider the following. The matter is that all these guys, in fact, live not here, but here, around 1, but I want to pass them there. So there is a shift by on W inverse, which takes this to that, and I would like to take the pullback of it, but I again get to here. So this one is called rho W. It depends on an element W. So actually what Davis proved is that he constructed this rho W, and his so proposition is that the direct sum of this rho W is exactly an isomorphism. So the required isomorphism is the required isomorphism. It is an isomorphism even on the level of cochains, and then it becomes isomorphism in cohomology. But it is an isomorphism even on the on the level of cochains. So this direct sum of these rho omegas goes to cochains of sigma. Look, it is not so easy. The matter is that this is a very non-trivial part. This pullback, if we have a cochain concentrated here, then its pullback will be concentrated not here, but in the whole this region. So here, the corresponding cochain will be concentrated in similar region here. No, K is not a small. K is full dimensional, of course. First,
Yeah, but it's
it's like
like neighborhood.
neighbor. Yeah, it's something like neighborhood of this point, but this is not a point. This intersection of mirrors is not a point. It is something difficult, complicated. Well. Well, let us understand. Just let us prove this. Let us prove this. To be precise, we need to do the following. I would like to add these chambers one by one. So I need some order of them. Just let us, of course, our Coxeter group is countable, so we just order elements of it. These are all elements of W, such that their lengths do not increase, do not decrease. So any order with this property. Of course, there are plenty of them. And I would like to add points, to add chambers one by one. So let us introduce the following notation. We can consider sigma n, which is the union of all chambers with I greater than n. All chambers which are far from 1. Then, of course, we can consider such pairs, sigma, sigma n, and we can take cohomology. And of course, I'm sorry, we have direct limit of this cohomology. Well, oh, so sorry, H star. And this is, of course, exactly compactly support cohomology of sigma. Again, this is true on the level of cochains. On the level of cochains, this is, let us write down it on the level of cochains. This is obvious. And then direct limit is an exact functor, so direct limits of if for non-coupledly generated cohomology, we would have inverse limit. And it is not true that inverse limit is an exact functor, but direct limit is an exact functor, so it is true for cohomology as well. Look, I claim that this rho omega in fact goes, so assume that we assume that this W is Wn. I claim, so sigma n is the union of all greatest. I claim that this rho omega in fact goes to C star of sigma n, and then here. Why? Well, first of all these part of this cone, except for this chamber, is in sigma n. They have the matter, they have great length. We have some number of mirrors which must be intersected when we go from 1 to W, and that intersect at least one more mirror. So we get into here. Well, and so in fact we can write down let us consider the following triple. We can consider the triple sigma, sigma n minus 1, sigma n. Well, sigma n minus 1 is this together with all greater, and sigma n are all only greater. And what we see? We have, of course, associated with this, we have an exact sequence of cochain groups. Which exact sequence of cochain groups? Cochains of sigma n minus 1. Sorry. Well, let us start with chain groups. I'm sorry for that. For chain groups, we have this one, yes? No. Well, what? I'm sorry. What is the exact sequence of cochain groups? We have cochain groups of sigma with respect to sigma n, then go to cochain groups of sigma with respect to sigma n minus 1, and then go restrict to sigma n minus 1. Well, for cochain groups, we have such exact sequence. These are all functions on cells of sigma, which vanish on sigma n.
Sigma n inside sigma n.
Yes.
So it's
At the end, yes, sigma n minus 1, sigma n.
yes. And
Yeah.
first should be sigma n minus 1.
Uh,
Because sigma n maps to
yes, I'm sorry. Yes, like that, yes. This is the standard sequence of cochain complexes, yes? And then, well, this one is obviously the same as C star of K of TW. The matter is that, look, this cell is in sigma n minus 1, but not in sigma n. All those cells are in sigma n, but all cells here are not in sigma n. All which, when we cross this one, we are not in sigma n. Not in sigma n, not in sigma n minus 1. We have also some parts of sigma n somewhere far from here, but this pair, actually we have a homeomorphism sigma n minus 1 quotient by sigma n is just the same as k quotient by k t of w. This is just the same. No, without any sum. Just for any w, we have this. Now, this w is of course wn. This is the element with number n. And what we see that, well, we always have such exact sequence, but now this rho w is the splitting homomorphism. It is easy to see that it splits the sequence. And hence, the middle term is this one, direct sum with that. And then by induction, we get the theorem. Well, actually, here there is some interesting point why it is actually splitting, why this combination is identity. And this is non-trivial since it incorporates this rather non-trivial pullback along projection. But look, suppose you have some cochain which lives here, which is a relative cochain of K with respect to this path. Let us move to here. It is a relative cochain of this chamber with respect to this path. We by this PQ sharp, we take the pullback. We obtain a relative cochain of the whole such union with respect to the boundary. But all other chambers here are closer to one than this one. So when we go to here, then we restrict to the initial cochain. That's that's the end of the computation. So we have proved the theorem. Well, to be honest, I cannot say to you now why I haven't illustrated to you why these cohomology with group ring coefficients are so important. So why this theorem is interesting. I understand that I do not have any time for that, and but my point was just to say that my point was more to demonstrate methods than the importance of this particular result. So this proof, it seems to me that it incorporates very well some cut zero technique, some topological technique, and some purely group technique, and so that's all. Well, I think that and of course it is of this concerns Coxeter groups, but it is of a special importance that these cohomology with group coefficients, with group ring coefficients, are the same for groups, for subgroups of finite order. This is useful not only for Coxeter groups. Of course, this is a general result, which is rather easy, but which is important. Well, so let us stop at this point. That's all.